Drop a ball and it falls, toss a rock, and it arcs back to Earth. We call this gravity, and for most of human history, we thought we understood it, a force pulling objects together, simple and invisible. But what if I told you that gravity isn't pulling anything at all? What if the ball doesn't fall because Earth yanks it downward, but because the ground rushes up to meet it through curved space? Today, we're diving deep into one of physics' most profound mysteries. Does gravity really bend the fabric of space-time, or have we been seduced by a compelling metaphor that might be hiding an even more mind-bending truth? If you're fascinated by the deepest questions about how our universe actually works, make sure to subscribe to this channel and give a thumbs up. Now let's begin. To understand whether gravity truly bends space-time, we first need to grasp what space-time even is. Before Einstein, space and time were considered separate, absolute entities. Space was the three-dimensional stage where events unfolded, and time was the universal clock ticking forward at the same rate for everyone, everywhere. Newton's laws of motion and gravity operated within this framework beautifully, predicting planetary orbits with remarkable precision. But this picture harbored hidden problems that wouldn't reveal themselves until scientists could make extraordinarily precise measurements. In 1905, Albert Einstein published his special theory of relativity, which shattered the Newtonian view. He demonstrated that space and time aren't separate but intimately connected. Different observers moving at different speeds would disagree on measurements of distance and duration. What one observer measures as a meter, another measures as slightly less. What one experiences as a second, another experiences as slightly more. Space and time are relative, their measurements depending on the observer's motion. But special relativity had a glaring limitation. It couldn't handle acceleration or gravity. Einstein spent the next decade wrestling with this problem, seeking a theory that would incorporate gravity into his relativistic framework. The breakthrough came through what he later called the happiest thought of my life. He realized that someone falling freely feels no gravity. Imagine you're in an elevator when the cable snaps. As you plummet, you float weightlessly, exactly as if gravity had vanished. Objects released from your hand drift beside you rather than falling. This led Einstein to a stunning insight. Gravity and acceleration are equivalent. You can't tell the difference between floating in deep space, far from any gravitational influence, and falling freely in a gravitational field. Similarly, standing on Earth's surface feels identical to being in a rocket accelerating through space at 9.8 meters per second squared. This equivalence principle became the cornerstone of his general theory of relativity, published in 1915 after years of mathematical struggle. General relativity describes gravity not as a force, but as the curvature of space-time itself. Massive objects like stars and planets warp the four-dimensional fabric of space and time around them, and other objects respond to this curvature by following the straightest possible paths through the warped geometry. What we perceive as gravitational attraction is actually objects moving along these curved paths, geodesics in the language of mathematics, through curved space-time. The metaphor most commonly used compares space-time to a rubber sheet. Place a bowling ball on a stretched rubber sheet and it creates a depression. Roll a marble nearby and it curves toward the bowling ball, not because the bowling ball pulls it, but because the marble follows the curved surface. This analogy helps visualize the concept, but also misleads in crucial ways we'll explore later. For now, it captures the essential idea. Mass curves space-time, and this curvature guides the motion of objects and even light itself. Einstein's equations, 10 interrelated differential equations of fiendish complexity, precisely describe how mass and energy curve space-time and how this curvature dictates motion. These equations have passed every observational test thrown at them over more than a century. But do they describe reality or merely predict observations accurately while the true nature of gravity remains hidden? The first test came quickly. Einstein's theory made a specific prediction about Mercury's orbit that Newton's gravity couldn't explain. Mercury, the innermost planet, orbits the Sun in an ellipse that slowly rotates. The point of closest approach shifts slightly with each orbit, a phenomenon called perihelion precession. Astronomers had measured this precession at 43 arcseconds per century, more than Newton's theory predicted. Various explanations were proposed, including an undiscovered planet called Vulcan orbiting inside Mercury's path. Einstein's equations predicted the anomalous precession exactly, with no adjustable parameters. The curvature of spacetime near the Sun's massive bulk affects Mercury more than the outer planets, causing the precise amount of extra precession observed. This wasn't a prediction made after the fact. The mathematics of general relativity necessarily produced this result. Mercury's orbit became the first evidence that space-time curvature might be more than mathematical convenience. But the most dramatic early test came in 1919, during a total solar eclipse. Einstein's theory predicted that starlight passing near the Sun would bend due to space-time curvature around our star. Newton's theory also predicted light bending. If light has momentum, the Sun's gravity should deflect it, but Einstein's theory predicted exactly twice the Newtonian deflection. The difference was small, just 1.75 arcseconds, but measurable during an eclipse when stars near the Sun's edge become visible. British astronomer Arthur Eddington led expeditions to Principe Island off West Africa and Sobral in Brazil to photograph stars near the Sun during the May 29th eclipse. Comparing these positions to photographs of the same star field taken months earlier when the Sun was elsewhere revealed the deflection. The results matched Einstein's prediction, not Newton's. Headlines around the world proclaimed the triumph of general relativity, making Einstein an international celebrity virtually overnight. However, modern analysis of Eddington's data reveals significant uncertainties. The measurements barely distinguished between the two predictions given the observational errors. The scientific community embraced general relativity partly because of these eclipse results, but also because the theory's mathematical elegance and explanatory power convinced theorists of its superiority. The eclipse observations provided suggestive evidence, but the case for curved space-time required much stronger confirmation. That confirmation has accumulated over subsequent decades through increasingly precise tests. Gravitational lensing, the bending of light by massive objects, has been observed countless times. In 1979, astronomers discovered the first gravitational lens, a quasar whose light was bent by an intervening galaxy, creating multiple images of the same distant object. Today, the Hubble Space Telescope and other observatories routinely observe spectacular lensing, including Einstein rings where distant galaxies appear as circular arcs wrapped around foreground galaxy clusters. The most famous Hubble image demonstrating lensing shows the galaxy cluster Abell 2118, where the combined mass of hundreds of galaxies warps space-time so dramatically that background galaxies appear stretched into arcs and multiple images. The distortion pattern exactly matches predictions from Einstein's equations. Astronomers use this lensing to map dark matter distribution, the invisible mass that doesn't emit light but reveals itself through gravitational effects, including space-time curvature. Speaking of how gravity behaves in the most extreme environments, if you are curious how gravity can escape from black holes, check out my video called "If Light Can't Escape a Black Hole, How Can Gravity?", where we explore this mind-bending paradox. The link is in the description and pinned on the comments. Gravitational time dilation provides another test. Clocks run slower in stronger gravitational fields, or more precisely, in regions where space-time curvature is more pronounced. This isn't a mechanical effect on clocks, but a genuine slowing of time itself. Atomic clocks flown on airplanes and satellites tick at measurably different rates than identical clocks on Earth's surface, exactly as general relativity predicts. The global positioning system relies on accounting for both special and general relativistic effects. GPS satellites orbit at about 20,000 kilometers altitude, where they move at approximately 14,000 kilometers per hour and experience weaker gravity than Earth's surface. Special relativity predicts their clocks run slower due to their motion, about 7 microseconds per day. General relativity predicts their clocks run faster due to weaker gravity, about 45 microseconds per day. The net effect is about 38 microseconds per day faster. This sounds tiny, but light travels about 30 centimeters per nanosecond. Without relativistic corrections, GPS errors would accumulate at about 10 kilometers per day, rendering the system useless. Every time your phone determines your location using GPS, it's confirming that spacetime curvature is real, or at least that Einstein's equations accurately describe whatever is actually happening. Gravitational waves provide perhaps the most direct evidence for spacetime's physical reality. Einstein's equations predict that accelerating masses create ripples in spacetime itself, waves of curvature that propagate at light speed. For decades, these waves remained theoretical, their effects too weak to detect even from cosmic cataclysms. But on September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO for short, detected gravitational waves from two colliding black holes 1.3 billion light-years away. The signal lasted only a fraction of a second, but its shape precisely matched predictions for two black holes spiraling together and merging. The waves alternately stretched and compressed space itself as they passed through Earth, stretching in one direction while compressing perpendicular to it. The effect was incredibly tiny. LIGO's 4-kilometer-long arms changed length by less than 1/10,000th the diameter of a proton. Yet this measurement was clear and unmistakable. Since that first detection, LIGO and its European counterpart Virgo have observed dozens of black hole mergers and several neutron star collisions. The gravitational wave signals match theoretical predictions with extraordinary precision. The 2017 Nobel Prize in Physics went to Rainer Weiss, Barry Barish, and Kip Thorne for LIGO's development and the gravitational wave discovery. These observations seem to confirm that space-time isn't just a mathematical abstraction, but a physical entity that can flex, ripple, and wave. Yet despite this overwhelming observational success, deep questions remain about whether we're truly seeing space-time curvature or something more subtle. The rubber sheet analogy, while helpful, fundamentally misleads. A rubber sheet is a two-dimensional surface embedded in three-dimensional space. It curves through that higher dimension, but space-time isn't embedded in anything higher. The curvature is intrinsic, describing how the geometry of space-time itself differs from flat Euclidean geometry. Moreover, what does it mean to say space is curved when we can't step outside space to view the curvature? We live within space-time, measuring distances and durations using rulers and clocks that are themselves affected by whatever curvature exists. It's like asking inhabitants of a two-dimensional world living on a sphere's surface to detect their world's curvature. They could do it, not by seeing the curvature from outside, but by measuring how geometry works. Draw a triangle on a sphere and its angles sum to more than 180 degrees. Travel in what seems a straight line long enough and you return to your starting point. Similarly, we detect space-time curvature not by observing it from outside, but by measuring how geometry differs from what we'd expect in flat space. Light travels the straightest possible paths, yet we see it curve near massive objects. Clocks at different gravitational potentials tick at different rates. Parallel paths that start out parallel gradually converge or diverge. These observations demonstrate that spacetime's geometry is non-Euclidean, but do they prove that something called spacetime actually exists as a physical fabric? Some physicists argue that spacetime curvature is merely a useful mathematical description, not a claim about physical reality. In this view, Einstein's equations accurately predict observations, but curved spacetime is just computational machinery, elegant mathematics that works without necessarily representing what's fundamentally real. Just as Ptolemy's epicycles predicted planetary positions without those epicycles being real, perhaps curved spacetime predicts observations without spacetime being an actual bendable fabric. This interpretation gains credibility when we consider that general relativity breaks down at certain extremes. Inside black holes, at the singularity where density becomes infinite, Einstein's equations produce nonsensical results, infinities that suggest the theory is incomplete. Similarly, at the Big Bang singularity, general relativity cannot describe conditions. These breakdowns hint that spacetime curvature might be an approximate description that works beautifully in most situations, but fails where quantum effects become dominant. The quest for quantum gravity, a theory uniting general relativity with quantum mechanics, has consumed theoretical physics for decades. Quantum mechanics describes the microscopic world of particles and fields, where reality is probabilistic and uncertainty reigns. General relativity describes spacetime and gravity, treating them as smooth, deterministic, classical entities. These frameworks are mathematically incompatible. Reconciling them requires either quantizing gravity or geometrizing quantum mechanics, and neither approach has yielded a complete, testable theory. String theory, one prominent candidate for quantum gravity, suggests that spacetime might be emergent rather than fundamental. In string theory's mathematical framework, the fundamental entities are tiny vibrating strings, and spacetime emerges from relationships between these strings. Just as temperature emerges from molecular motion, there's no such thing as the temperature of a single molecule, spacetime might emerge from quantum string interactions. If true, asking whether gravity bends spacetime becomes like asking whether heat bends temperature, a category error because spacetime wouldn't be a thing that exists to bend. Loop quantum gravity, another approach, treats spacetime itself as quantized, built from discrete units at the Planck scale, approximately 10 to the negative 35 meters. At this incomprehensibly tiny scale, space might be granular rather than continuous, woven from quantum loops that create spacetime's fabric. In this picture, curvature would represent how these quantum loops connect and arrange themselves. Spacetime wouldn't be smoothly curved, but rather built from discrete quantum chunks, whose arrangement creates the appearance of smooth curvature at larger scales. Neither string theory nor loop quantum gravity has made testable predictions confirmed by experiment, so they remain speculative. But they illustrate how cutting-edge physics questions whether spacetime is fundamental or emergent, whether curvature is real or approximate. The observational success of general relativity doesn't settle these questions. Newtonian gravity worked magnificently for centuries before being recognized as an approximation to Einstein's theory. Perhaps Einstein's curved spacetime will likewise be recognized as an approximation to some deeper quantum theory. Let's examine what bending spacetime means more carefully. In Einstein's mathematics, spacetime is a four-dimensional manifold, a continuous space where each point represents an event with 3 spatial coordinates and 1 time coordinate. The metric tensor, a mathematical object describing distances and angles, encodes spacetime's geometry. In flat spacetime, far from gravitational sources, this metric takes a simple form, the Minkowski metric of special relativity. Near massive objects, the metric changes describing how distances and time intervals differ from flat space. Curvature quantifies how the metric varies from place to place. The Riemann curvature tensor, a fearsome mathematical beast with 20 independent components in 4 dimensions, completely characterizes spacetime's curvature. Einstein's field equations relate this curvature to the distribution of mass, energy, momentum, and stress. Solving these equations for a given mass distribution yields the metric from which geodesics, the paths objects and light follow, can be calculated. This mathematical machinery works brilliantly. Feed in the sun's mass, and out come planetary orbits. Feed in a black hole's mass and angular momentum, and out come the properties of its event horizon and the bizarre phenomena near it. Feed in the mass-energy distribution of the entire universe, and out come cosmological models describing cosmic expansion. The mathematics is consistent, elegant, and empirically successful. But does it describe reality's fundamental structure? Consider an analogy from earlier physics. Before quantum mechanics, we described heat as a fluid called caloric that flowed from hot to cold. This caloric theory made accurate predictions and enabled practical calculations. Eventually, we realized heat isn't a fluid but molecular kinetic energy. The theory was predictively accurate but ontologically wrong. Similarly, Newtonian gravity described gravity as a force and made excellent predictions, but we now understand it as space-time curvature. The theory worked while being fundamentally wrong about gravity's nature. Might we be making the same mistake with curved space-time? Perhaps some future theory will reveal that what we call space-time curvature is actually something else entirely: quantum entanglement structure, information geometry, or something we haven't yet imagined. The observations would remain: light deflection, time dilation, gravitational waves, but their fundamental explanation would differ from Einstein's geometric picture. Some hints that space-time might not be fundamental come from black hole thermodynamics and the holographic principle. In the 1970s, physicist Stephen Hawking discovered that black holes emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation means black holes have temperature and entropy, thermodynamic properties usually associated with systems containing many particles. But what are the microscopic constituents of a black hole that give it entropy? Jacob Bekenstein had earlier proposed that a black hole's entropy is proportional to its event horizon area, not its volume. This surprised physicists because entropy typically relates to volume. More space means more possible arrangements of particles. The area law suggested something profound. Perhaps all the information about what fell into a black hole is encoded on its 2-dimensional surface, not throughout its 3-dimensional volume. This led to the holographic principle, which suggests that the information content of any region of space can be encoded on its boundary surface. Our 3-dimensional universe, in this view, might be a holographic projection of information encoded on a distant 2-dimensional surface. If true, our perception of 3 spatial dimensions might be an illusion, a useful description that emerges from fundamentally 2-dimensional quantum information. The holographic principle receives support from the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. This mathematical relationship connects a 5-dimensional gravitational theory to a 4-dimensional quantum field theory without gravity. The gravitational theory includes curved spacetime and black holes. The quantum field theory has no gravity and no extra dimension. Yet the two theories are mathematically equivalent, different descriptions of the same physics. This correspondence suggests that space-time and gravity might be emergent phenomena arising from quantum entanglement in a lower dimensional theory without gravity. Changing the entanglement structure in the quantum theory corresponds to changing space-time geometry in the gravitational theory. In this picture, asking whether gravity bends space-time is like asking whether software runs on hardware. It's not wrong, but it mistakes an emergent phenomenon for something fundamental. Other approaches also question spacetime's fundamental reality. Entropic gravity, proposed by Erik Verlinde, suggests that gravity emerges from statistical thermodynamics, much as pressure emerges from molecular collisions. In this view, what we call gravitational attraction is actually an entropic force arising from quantum information changes. Space might not fundamentally exist. Instead, gravity emerges from the tendency of quantum systems to maximize entropy. These radical ideas remain controversial and incomplete. They haven't produced testable predictions that clearly distinguish them from standard general relativity, but they illustrate that leading physicists seriously question whether spacetime is fundamental or emergent, whether curvature is real or effective. The fact that Einstein's equations work doesn't prove their ontology. What they say about reality's ultimate nature is correct. Let's return to observations and ask, what exactly do gravitational wave detections tell us? LIGO measures changing distances between mirrors as gravitational waves pass. The standard interpretation is that spacetime itself stretches and compresses, carrying the mirrors with it. But could something else produce the same observable effect? In principle, yes. Any theory that predicts traveling disturbances that alternately stretch and compress space, or produce effects identical to such stretching, would match observations. Modified gravity theories, which alter Einstein's equations at cosmic scales to explain dark energy without introducing new substances, must reproduce gravitational wave observations. Some succeed, others are ruled out by the combination of gravitational and electromagnetic observations of neutron star mergers. On August 17, 2017, LIGO and Virgo detected gravitational waves from colliding neutron stars. Remarkably, telescopes observed light from the same event: gamma rays, X-rays, ultraviolet, optical, infrared, and radio waves across the electromagnetic spectrum. The gravitational waves arrived at Earth 1.7 seconds before the gamma ray burst, having traveled 130 million light-years. This observation constrained the speed of gravitational waves to equal the speed of light to within 1 part in 10 to the 15th, extraordinary precision. Many modified gravity theories predicted gravitational waves traveling at different speeds than light. Those theories are now ruled out. The observation also confirmed that gravitational waves don't significantly interact with matter during their journey. They passed through galaxies, dust, and gas clouds without noticeable absorption or scattering. These properties match general relativity's predictions exquisitely. Gravitational waves are ripples in spacetime itself, not disturbances traveling through space, so they travel at light speed and don't interact with matter. Alternative theories must reproduce these properties while explaining gravity differently, a difficult challenge. Each successful test narrows the space for alternative theories, strengthening the case that Einstein's description captures something deeply true about reality. Yet the quantum gravity problem persists. General relativity predicts singularities, points of infinite density and curvature, at black hole centers, and the Big Bang. Physics has learned that infinities usually signal where theories break down. Quantum mechanics should somehow smooth these singularities, but we don't know how because we lack a complete quantum theory of gravity. Inside black holes, beyond the event horizon, space-time curvature becomes so extreme that paths pointing toward the future necessarily lead toward the singularity. You can't avoid it any more than you can avoid tomorrow. The singularity is in your future, not a place in space, but a moment in time. This bizarre consequence of curved space-time geometry produces one of the strangest predictions in physics. Time and space swap roles inside the event horizon. Outside a black hole, you can move freely in space, left, right, forward, backward, but time marches inexorably forward. Inside the event horizon, the situation reverses in a sense. You can't avoid moving toward the singularity any more than you can avoid moving toward the future, and the radial direction toward the singularity becomes time-like rather than space-like. This isn't mere wordplay, but a consequence of how Einstein's equations describe extreme space-time curvature. The geometry itself becomes so warped that our usual concepts of space and time cease to apply normally. Does this mean space-time curvature is real? The mathematics consistently describes observations, but at these extremes, we suspect the theory breaks down. Quantum effects should dominate at the Planck scale, roughly 10 to the negative 35 meters, where quantum uncertainty in position becomes comparable to the distance itself. Near singularities, curvature becomes so extreme that Planck-scale quantum effects cannot be ignored, yet general relativity is a classical theory that doesn't include quantum mechanics. This suggests that at the deepest level, space-time might dissolve into quantum foam, a seething froth of quantum geometry where space and time lose their classical meanings. In this regime, asking whether space-time is curved becomes meaningless because space-time itself might not exist as a coherent concept. What we perceive as smooth space-time curvature might be an averaged, large-scale description of this underlying quantum chaos, much as a smooth liquid surface emerges from countless chaotic molecular motions. Loop quantum gravity attempts to describe this quantum geometry directly. In this framework, space is woven from quantum loops called spin networks, where geometry is quantized in discrete chunks. Area and volume come in minimum units, roughly the Planck area and Planck volume. Curvature emerges from how these quantum loops connect and interweave. The theory suggests that singularities are avoided because geometry cannot become infinitely curved. It reaches a maximum curvature determined by Planck-scale quantum effects. If loop quantum gravity is correct, general relativity's smooth curved spacetime is an approximation that emerges when averaging over vast numbers of quantum loops. Much as a beach appears smooth from a distance despite being made of discrete sand grains. The curvature would be real in the sense that the arrangement of quantum loops creates genuine geometric effects, but space-time wouldn't be a continuous fabric. It would be built from discrete quantum bits of geometry. String theory takes a different approach, suggesting that what we perceive as particles are actually tiny vibrating strings. Different vibration patterns correspond to different particles, electrons, quarks, photons, and crucially, gravitons, the hypothetical quantum particles that would carry gravitational force. In string theory's mathematical framework, spacetime emerges from string interactions and is not fundamental. The mathematics of string theory requires extra spatial dimensions beyond the 3 we observe, typically 6 or 7 additional dimensions curled up at scales far too small to detect. The geometry of these hidden dimensions determines the properties of particles and forces in our observable 4-dimensional spacetime. In this exotic picture, the curvature of our familiar spacetime reflects the geometry of extra dimensions and string interactions. String theory faces a challenge called the landscape problem. The mathematics allows roughly 10 to the 500 different possible configurations of the extra dimensions, each giving rise to a different 4-dimensional physics. This enormous number of possibilities makes it difficult to extract testable predictions. Critics argue that a theory predicting almost anything predicts nothing. Proponents counter that perhaps our universe is just one of many possible configurations, possibly explaining why physical constants have the values they do. We exist in a universe compatible with our existence. Both loop quantum gravity and string theory remain incomplete and untested. Neither has made specific predictions confirmed by experiment. This leaves us in an unusual situation. We have a spectacularly successful classical theory, general relativity, that we know must break down under extreme conditions, but we don't know what replaces it. The question of whether space-time is really curved or whether curvature is an effective description of something deeper remains genuinely open. Let's consider what we can say with confidence. First, Einstein's geometric description of gravity works extraordinarily well across an enormous range of conditions, from GPS satellites to neutron stars to galaxy clusters to the observable universe as a whole. Whatever gravity ultimately is, it manifests in ways precisely captured by curved space-time geometry in these regimes. Second, this geometric description isn't merely mathematical convenience. Gravitational waves are detected as actual disturbances propagating through space, carrying energy and momentum. They produce measurable effects, oscillating distances between separated masses that match predictions for ripples in space-time geometry. Something physically real is waving, whether we call it space-time or something else. Third, the equivalence principle, the foundation of general relativity, is tested to extraordinary precision. The microscope satellite, which completed its mission in 2018, tested whether different materials fall at precisely the same rate in a gravitational field. It found no difference to 1 part in 10 to the 15th. This confirms that gravity acts on all matter and energy identically, strongly supporting the geometric interpretation where objects simply follow space-time's curvature. Fourth, gravitational time dilation is real and measurable. Atomic clocks at different heights run at different rates. GPS wouldn't work without accounting for this. Observers at different gravitational potentials genuinely experience time at different rates. This isn't illusion or mathematical artifact, but observable physical reality. Something about the structure of space and time varies with gravitational environment. Fifth, gravitational lensing demonstrates that light follows curved paths near massive objects. We observe this curvature in spectacular detail through Hubble images and gravitational wave observations. Light has no mass, so Newtonian gravity predicts minimal deflection. Einstein's theory predicts exactly the deflection observed. Light follows space-time's geometry, whatever that geometry fundamentally represents. These observations collectively demonstrate that gravity manifests as geometric effects on space and time. Whether this geometry is fundamental or emergent from deeper quantum structures remains uncertain, but the geometric description captures something genuinely real about how gravity operates. The question isn't whether Einstein was completely wrong, he clearly wasn't, but whether his description is complete and fundamental, or effective and emergent. Consider an analogy from condensed matter physics. Physicists describe certain materials using concepts like phonons, quantum particles representing vibrations in crystal lattices. Phonons aren't fundamental particles like electrons or quarks. They're collective excitations emerging from many atoms vibrating together. Yet phonons are real. They carry energy and momentum, scatter other particles, and can be experimentally detected. Asking whether phonons are real gets a nuanced answer. They're not fundamental constituents of reality, but they're genuine physical phenomena with measurable properties. Space-time curvature might be similar. It might not be fundamental. Perhaps it emerges from quantum entanglement, information geometry, or string dynamics. But it's real in the sense that it has measurable physical consequences and accurately describes gravitational phenomena across vast scales. The mathematical framework of curved spacetime captures something true about reality's structure, even if deeper layers underlie this geometric description. This perspective reconciles seemingly contradictory viewpoints. Yes, spacetime curvature is real. It describes actual physical phenomena and makes testable predictions confirmed by observation. No, it might not be fundamental. Quantum gravity might reveal spacetime as emergent. Both statements can be true simultaneously because real and fundamental mean different things. The Laser Interferometer, space antenna, LISA, planned for launch in the 2030s, will detect gravitational waves from space, opening new observational windows. LISA will observe supermassive black hole mergers, extreme mass ratio in spirals where stellar mass objects spiral into million solar mass black holes, and potentially signals from the early universe. These observations will test general relativity in regimes currently inaccessible, potentially revealing deviations that hint at quantum gravity effects. Ground-based gravitational wave detectors continue upgrading. LIGO and Virgo are being enhanced to increase sensitivity. The Kagra detector in Japan, built underground to reduce seismic noise, began operations in 2020. India is constructing LIGO India, expanding the global network. More detectors improve directional resolution and increase detection confidence. Each new gravitational wave observation tests whether ripples propagate exactly as Einstein's equations predict. Pulsar timing arrays offer another gravitational wave detection method. Pulsars, rapidly rotating neutron stars, emit radio beams that sweep across Earth like lighthouse beams, creating precisely regular pulses. Gravitational waves passing between Earth and pulsars alter the pulse arrival times in characteristic ways. By monitoring many pulsars across the sky, astronomers can detect low-frequency gravitational waves from supermassive black hole mergers and potentially from cosmic inflation. In June 2023, multiple pulsar timing arrays announced detection of a gravitational wave background, a cosmic hum of overlapping gravitational waves likely from countless supermassive black hole mergers throughout cosmic history. This observation opens yet another window on the universe, allowing us to probe gravitational phenomena on scales from meters to the observable universe's entire extent. Each observation further constrains theories of gravity. Modified gravity theories must reproduce all these varied observations: planetary orbits, gravitational lensing, time dilation, gravitational waves at multiple frequencies, cosmic expansion, and more. Einstein's general relativity passes every test. Alternative theories that modify gravity to explain dark matter or dark energy without introducing new substances face increasingly tight constraints. For instance, modified Newtonian dynamics, MOND, attempts to explain galactic rotation curves without dark matter by altering gravity's behavior at low accelerations. While MOND successfully matches galaxy rotation data, it struggles with galaxy cluster dynamics and gravitational lensing. The bullet cluster observation, showing gravitational lensing centered on locations separated from visible matter, strongly challenges MOND. The cluster collision separated dark matter from ordinary matter, revealing dark matter through its gravitational lensing despite being invisible. MOND has difficulty explaining this observation, while dark matter naturally does. Emergent gravity theories face similar challenges. They must reproduce general relativity's successes while explaining observations currently attributed to dark matter and dark energy. So far, no alternative theory succeeds as comprehensively as Einstein's curved spacetime plus dark matter and dark energy. This doesn't prove the standard model is ultimately correct, but it demonstrates the difficulty of replacing Einstein's geometric framework. The cosmological constant problem illustrates tensions between general relativity and quantum mechanics. Quantum field theory predicts that empty space, vacuum, contains energy from quantum fluctuations. This vacuum energy should act like Einstein's cosmological constant, contributing to cosmic expansion. But the predicted value exceeds observations by roughly 120 orders of magnitude, the worst prediction in physics history. Something prevents most quantum vacuum energy from gravitating, or the calculation is profoundly wrong, or we misunderstand vacuum energy's nature. This problem suggests that space-time, quantum fields, or both, are not what they seem at the deepest level. The resolution might reveal that space-time curvature is emergent rather than fundamental, that quantum field theory requires modification, or that we need entirely new concepts. Dark energy, whatever drives cosmic acceleration, comprises about 68% of the universe's energy density. We don't know what it is. The simplest explanation is Einstein's cosmological constant, a constant energy density of empty space itself. But why would this constant have precisely the tiny value observed rather than the enormous value quantum theory predicts? Alternative explanations include quintessence, a dynamic field varying over space and time, or modifications to general relativity on cosmic scales. The Dark Energy Spectroscopic Instrument, or DESI, is mapping millions of galaxies to measure cosmic expansion history and constrain dark energy's properties. The Nancy Grace Roman Space Telescope, launching in the mid-2020s, will study dark energy through multiple complementary methods. These observations aim to determine whether dark energy is truly constant or changes over cosmic time. Dark matter presents a parallel mystery. About 27% of the universe's energy density is dark matter, revealing itself through gravitational effects, galaxy rotation curves, gravitational lensing, cosmic structure formation, but not interacting electromagnetically. We don't know what dark matter particles are, though leading candidates include WIMPs, weakly interacting massive particles, and axions. Experiments worldwide search for these particles, so far without definitive detection. Some physicists wonder whether dark matter and dark energy indicate not new substances, but that our understanding of gravity requires modification. Perhaps general relativity, though accurate on solar system scales, breaks down on galactic or cosmic scales. Modified gravity theories attempt this, though none succeeds as comprehensively as general relativity with dark matter and dark energy. The interplay between observational evidence and theoretical frameworks shapes our understanding. Observations drive theory development, while theories guide what observations to pursue. General relativity emerged from theoretical considerations, Einstein's quest for a relativistic theory of gravity, yet it made testable predictions that observations confirmed. Similarly, quantum mechanics was partially driven by experimental puzzles, blackbody radiation, the photoelectric effect, that classical physics couldn't explain. Quantum gravity remains stubbornly theoretical. We lack experimental puzzles that clearly demand quantum gravity for resolution, though black hole information paradoxes and cosmological singularities hint at incompleteness. No tabletop experiment can probe Planck-scale physics where quantum gravity becomes essential. We must rely on astronomical observations, black holes, neutron stars, the early universe, or hope that quantum gravity's mathematical consistency uniquely determines the theory. String theory emerged from mathematical consistency requirements. Attempts to formulate a quantum theory of particles led to mathematics requiring strings instead. The theory's internal consistency demanded extraspatial dimensions and naturally included gravity through graviton string vibrations. But string theory makes few testable predictions at accessible energies, leading some to question whether it's science or mathematics. Loop quantum gravity emerged from attempting to quantize general relativity directly, preserving its geometric character while incorporating quantum mechanics. This approach treats spacetime geometry as the fundamental quantum variable, yielding predictions like discrete area and volume, bounded curvature, and singularity resolution. But extracting testable predictions from the mathematics has proved difficult. Other quantum gravity approaches exist: causal sets, asymptotic safety, causal dynamical triangulation, each with mathematical appeal and conceptual motivation. This diversity illustrates that we don't yet know how to quantize gravity or whether quantization is even the right approach. Perhaps gravity resists quantization because space-time is emergent, not fundamental. Perhaps a radically different framework is needed. The question, does gravity really bend space-time, thus has layers of meaning. Operationally, yes, Einstein's geometric description accurately predicts all gravitational phenomena we've observed. Mathematically, yes, the curvature formalism provides precise, testable predictions. Observationally, yes, gravitational lensing, time dilation, gravitational waves, and countless other phenomena match curvature predictions. But fundamentally, here uncertainty remains. Is space-time a real physical fabric that mass and energy curve? Or is curvature an effective description emerging from deeper quantum structures? Is geometry fundamental or emergent? These questions remain open because we lack a complete theory of quantum gravity and the experimental data to test competing frameworks. This uncertainty doesn't diminish general relativity's achievement. Einstein gave us a framework that works spectacularly well across vast ranges of scale and condition. Whether space-time is fundamental or emergent, Einstein's equations capture how gravity manifests in our world with extraordinary precision. Future quantum gravity theories must reproduce these successes while extending to regimes where quantum effects dominate. Consider analogies from physics history. Newtonian mechanics works magnificently for everyday objects, spacecraft navigation, and planetary orbits. We now know it's an approximation to relativistic mechanics, yet engineers use Newtonian physics routinely because it's accurate enough for most applications. Similarly, classical electromagnetism describes electricity, magnetism, and light beautifully, yet quantum electrodynamics is the deeper theory. The classical theory works because it's the appropriate limit of the quantum theory. General relativity might stand similarly to some future quantum gravity theory. Einstein's curved spacetime would be the classical limit, the appropriate description when quantum effects are negligible, which includes virtually all observable gravitational phenomena. Just as quantum mechanics reduces to classical mechanics for large, massive objects, quantum gravity would reduce to curved spacetime geometry on large scales. If this picture is correct, then spacetime curvature is real, in the same sense that classical phenomena are real, not fundamental ontology, but genuine effective description. Temperature is real, even though it's fundamentally molecular kinetic energy. Solidity is real, even though it emerges from quantum wave function repulsion. Spacetime curvature could be real even if it emerges from quantum entanglement geometry or string interactions. This perspective makes the question, does gravity really bend spacetime, less about binary true-false and more about levels of description. At the level where general relativity applies, gravity absolutely bends spacetime. That's what the mathematics says and what observations confirm. At deeper levels where quantum effects dominate, spacetime itself might dissolve into quantum foam or emerge from string dynamics, making bending spacetime less meaningful. The philosophical implications run deep. For centuries, we considered space and time as absolute backdrops where physics unfolds. Einstein revealed they're dynamical, influenced by matter and energy, warping and flexing in response to mass distribution. This shift from space as stage to space as actor fundamentally changed how we understand reality's structure. If quantum gravity reveals spacetime as emergent rather than fundamental, we'll undergo another conceptual revolution. Just as Einstein relativized space and time, showing they're not absolute but observer-dependent, quantum gravity might show they're not fundamental but emergent from quantum information or string interactions. Each revolution strips away layers we thought were bedrock, revealing deeper structures underneath. Yet some structures seem genuinely fundamental. Quantum mechanics' probabilistic nature and wave-particle duality appear essential to reality at small scales. The speed of light as a cosmic speed limit seems fundamental to causality's structure. Conservation laws, energy, momentum, angular momentum, reflect deep symmetries in physical law. Perhaps some aspects of general relativity also reflect fundamental features, even if space-time itself is emergent. The equivalence principle, that gravitational and inertial mass are identical, has been tested to extraordinary precision and shows no violation. This principle motivated Einstein's geometric approach and seems deeply connected to gravity's nature. Even if space-time is emergent, whatever gravity fundamentally is must preserve this equivalence. Similarly, gravitational waves propagate at light speed, and light follows null geodesics. These features likely persist in any quantum gravity theory. Different quantum gravity approaches make different suggestions about what's fundamental. Loop quantum gravity treats geometric quantities, area, volume, angles, as fundamental quantum variables, suggesting geometry is more basic than we thought. String theory makes vibrating strings fundamental, with geometry emerging from string relationships. Other approaches treat information or causal structure as fundamental, with space-time emerging from these. Determining which approach is correct requires experimental data currently unavailable. We need observations revealing quantum gravity effects, perhaps in black hole evaporation, early universe cosmology, or exotic astrophysical phenomena. The Event Horizon Telescope, which imaged black hole shadows in M87 and our Milky Way's center, might eventually detect quantum gravity signatures in black hole structures. The black hole information paradox remains a key puzzle. When matter falls into a black hole, what happens to information about its quantum state? Hawking radiation appears thermal, random, and carrying no information about what fell in, but quantum mechanics says information cannot be destroyed. Does it escape in subtle correlations in Hawking radiation? Is it stored on the event horizon? Does it remain inside until the black hole evaporates, then escape in a final burst? Or do we need to revise quantum mechanics? Recent work suggests information might escape through quantum entanglement between Hawking radiation particles and the black hole interior. The mathematics involves holography and quantum error correction codes, suggesting deep connections between quantum information, geometry, and gravity. Resolving the paradox might reveal whether space-time is fundamental or emergent and how quantum mechanics and gravity ultimately reconcile. Another puzzle involves singularities, points where general relativity predicts infinite curvature and density. The Penrose-Hawking singularity theorems prove that singularities are generic features of general relativity, not artifacts of simplified models. Any collapsing star massive enough forms a black hole with a central singularity. The Big Bang was a cosmological singularity. Classical general relativity predicts its own breakdown at these points. Most physicists believe quantum gravity smooths singularities, preventing infinite curvature through quantum effects. Loop quantum gravity explicitly shows this. Curvature reaches a maximum determined by Planck scale quantum geometry, then bounces, potentially producing a new expanding phase. This might resolve the Big Bang singularity, replacing it with a big bounce connecting our universe to a previous contracting phase. String theory approaches singularity resolution differently, often invoking extra dimensions or stringy corrections that smooth apparent singularities. Neither approach is observationally confirmed, so singularities remain theoretical puzzles, hinting at incompleteness. Observations of primordial gravitational waves from the early universe might someday reveal whether the Big Bang was a true singularity or a quantum bounce. The cosmic microwave background, radiation from when the universe became transparent 380,000 years after the Big Bang, carries imprints of earlier physics. Inflation theory predicts specific patterns in temperature fluctuations, beautifully confirmed by observations from COBE, WMAP, and Planck satellites. These patterns reveal quantum fluctuations stretched to cosmic scales by inflation's exponential expansion. Inflation also predicts primordial gravitational waves, ripples in space-time generated during the inflationary epoch. These waves would imprint a distinctive polarization pattern in the cosmic microwave background called B modes. The BICEP and Keck array experiments at the South Pole search for this signature. A detection would confirm inflation and provide a window into physics at energies approaching the Planck scale, possibly revealing quantum gravity effects. So far, primordial gravitational waves remain undetected, though instrumental sensitivity continues improving. The Simons Observatory and CMBS-4 experiment represent next-generation efforts to detect these signals. Success would represent a triumph of theoretical physics, confirming predictions about processes occurring in the universe's first fraction of a second, governed by physics far beyond our ability to recreate in laboratories. The interplay between theory and observation in cosmology is unique. We cannot experiment on the universe or rerun cosmic history. We observe a single universe at a single epoch, trying to reconstruct its past and predict its future from present conditions. This makes cosmology more like historical science, forensic reconstruction of past events from remaining evidence, than experimental physics. Yet cosmology has become remarkably precise. We know the universe's age, 13.8 billion years, to better than 1% accuracy. We know its composition, roughly 5% ordinary matter, 27% dark matter, 68% dark energy. We know its geometry is flat within measurement precision. We've mapped cosmic structure across billions of light-years and back to when the universe was a few percent its current age. This precision cosmology relies fundamentally on general relativity. Cosmic expansion, gravitational lensing surveys, cosmic microwave background analysis all use Einstein's equations. If those equations didn't accurately describe gravity, cosmology's successes would be miraculous coincidences. The fact that observations across vastly different scales and epochs consistently match predictions from a single theoretical framework, general relativity plus the cosmological principle, powerfully validates the curved space-time picture. Yet mysteries remain. We don't know what dark matter and dark energy are. We don't understand why the cosmological constant has its observed value. We can't observe the universe before the cosmic microwave background's release. We don't know if the universe is finite or infinite, whether it's one of many in a multiverse, or what happened at the initial singularity. General relativity describes observations beautifully, but leaves fundamental questions unanswered. Perhaps these mysteries will be resolved within general relativity's framework through discovering dark matter particles and understanding dark energy's nature. Or perhaps they signal that Einstein's theory, though accurate, is incomplete, an effective description that breaks down under extreme conditions or requires extension to encompass quantum phenomena. Time and further observations will tell. What can we conclude about whether gravity really bends space-time? The evidence overwhelmingly supports Einstein's geometric description as accurate within its domain of applicability. Gravitational phenomena, from planetary orbits to gravitational waves to cosmic expansion, are precisely described by curved space-time geometry. This isn't merely mathematical convenience, but reflects something genuine about gravity's nature. However, whether space-time is fundamentally a bendable fabric or whether curvature emerges from deeper quantum structures remains unknown. General relativity is a classical theory that breaks down where quantum effects dominate. Its ultimate relationship to quantum mechanics remains mysterious despite decades of theoretical effort. Future observations might reveal deviations from Einstein's predictions that hint at quantum gravity's nature. The question highlights the difference between operational and ontological truth. Operationally, Spacetime curvature is true. It describes observations and makes accurate predictions. Ontologically, regarding what fundamentally exists, we're uncertain. Spacetime might be fundamental or it might be emergent. Both possibilities remain open. This uncertainty shouldn't diminish our appreciation for general relativity's achievement. Einstein gave us a framework of breathtaking elegance and power, unifying space, time, matter, and gravity into geometric relationships. That this framework emerged from pure thought, reasoning about the equivalence of gravity and acceleration, combined with mathematical consistency requirements, yet describes nature with extraordinary precision, ranks among humanity's greatest intellectual achievements. Moreover, general relativity transformed how we understand reality. Before Einstein, we imagined space and time as fixed stages where events unfold. Einstein revealed them as dynamic participants in cosmic drama, warping and flexing in response to matter and energy. This shift from absolute to relational, from fixed to dynamic, fundamentally altered our worldview. If quantum gravity reveals space-time as emergent, we'll experience another such shift. Just as Einstein showed space and time are relative rather than absolute, quantum gravity might show they're emergent rather than fundamental. We'd need new concepts to understand reality's deepest layer, perhaps quantum entanglement geometry, information networks, or structures we haven't yet imagined. Science progresses through such conceptual revolutions. Each revolution preserves successful predictions of previous theories while extending understanding into new regimes. Newtonian mechanics remains valid for everyday objects despite being superseded by relativity. Classical electromagnetism works beautifully for most applications despite quantum electrodynamics being more fundamental. Similarly, Einstein's curved space-time will remain the appropriate description for most gravitational phenomena, even if quantum gravity reveals deeper structures. The practical implications of general relativity pervade modern life. GPS navigation depends on relativistic corrections. Gravitational wave astronomy opens new windows on the cosmos. Tests of general relativity advance our understanding of fundamental physics. Even if space-time is ultimately emergent, Einstein's equations will remain the go-to framework for describing gravity across scales from satellites to galaxies. The story of curved space-time illustrates science's self-correcting nature. Einstein didn't declare Newton wrong. He showed Newtonian gravity is an approximation valid at low speeds and weak fields. Future quantum gravity theories won't declare Einstein wrong, but will show curved space-time is an approximation valid at large scales and weak quantum effects. Each theory encompasses its predecessors as limiting cases. This progression toward deeper understanding characterizes humanity's scientific journey. We've progressed from Earth-centered cosmology to heliocentric models to understanding our Sun as one star among billions in one galaxy among trillions. We've progressed from thinking matter is continuous to atomic theory to quantum mechanics to the standard model of particle physics. Each step revealed that reality is stranger and more subtle than we imagined. Curved space-time represents our current understanding of gravity's nature, a geometric description that works magnificently within its domain. Whether it's ultimately fundamental or emergent from quantum structures, it captures genuine features of how gravity manifests in our universe. Future discoveries might reveal deeper layers, but Einstein's geometric insight will remain a crucial piece of our understanding. As you go about your daily life, remember that you're moving through curved space-time. Earth's mass warps the geometry around it, creating what we experience as gravity. Your weight isn't Earth pulling you down, but rather you resisting space-time's curvature that naturally guides objects toward Earth's center. Time flows slightly slower at your feet than at your head due to gravitational time dilation, though the effect is far too small to notice. When you look at stars at night, you're seeing light that followed curved geodesics through space-time, bent by the sun's gravity, interstellar gas clouds, and the galaxy's mass distribution. The constellations you see appear in specific patterns partly because of how light curves through space. Gravitational lensing by our Milky Way and distant galaxies affects which stars and galaxies we can observe and how they appear. The GPS satellite signals your phone receives are time-stamped using atomic clocks running faster than ground clocks due to weaker gravity at orbital altitude. Without accounting for both special and general relativistic time dilation, effects of motion, and gravity on time's passage, position errors would accumulate at about 10 kilometers per day. Every navigation direction, every location pin, every mapped route depends on understanding space-time curvature. The universe itself expands as space-time stretches between galaxy clusters. This expansion isn't galaxies moving through space, but space itself growing, carrying galaxies along. The most distant observable objects recede faster than light as space expands between us, not violating relativity because they're not moving through space faster than light, but rather being carried by expanding space. This cosmic expansion is curved space-time evolving over time, described by Einstein's equations applied to the universe as a whole. Black holes represent space-time curvature's most extreme manifestation. At the event horizon, space-time curvature becomes so severe that escape requires exceeding light speed, which nothing can do. Inside the horizon, all paths lead to the singularity where curvature becomes infinite and Einstein's equations break down. Black holes are regions where space-time geometry becomes so warped that our normal concepts of space and time cease to apply. Gravitational waves passing through Earth oscillate space-time geometry at our location, alternately stretching and compressing distances by amounts far smaller than atomic nuclei. LIGO detects these tiny distortions, revealing cosmic cataclysms billions of light-years away, black holes colliding, neutron stars merging, possibly cosmic strings vibrating if they exist. Each detection confirms that space-time ripples are real, propagating phenomena carrying energy and information. All these phenomena, GPS corrections, cosmic expansion, black holes, gravitational waves, are precisely described by Einstein's geometric theory. Whether space-time is fundamentally a bendable fabric or these phenomena emerge from deeper quantum structures, the geometric description captures something profoundly true about how gravity works in our universe. The question of whether gravity really bends space-time ultimately asks, is our best current description of gravity fundamentally correct, or is it an effective theory that will be superseded? History suggests that successful theories are typically approximations to deeper theories. Newtonian mechanics approximates relativity, classical physics approximates quantum mechanics, perhaps curved space-time approximates some quantum geometric description we haven't yet discovered. But approximations aren't wrong, they're accurate within their domains. Newtonian mechanics correctly describes projectile motion, planetary orbits, and engineering problems. It's not false, it's incomplete. Similarly, curved space-time correctly describes gravitational phenomena from laboratory scales to cosmic scales. It may be incomplete, requiring quantum corrections at Planck scales, but it's accurate for phenomena we can currently observe. So does gravity really bend space-time? Within the framework of general relativity, absolutely yes. The geometric description isn't optional or interpretive, it's what the mathematics says, and observations confirm it. Mass and energy curve, space-time geometry, and this curvature guides the motion of objects and light. This is as true as any statement in physics can be. At a deeper level, we don't know if space-time is fundamental or emergent. Quantum gravity research suggests space-time might emerge from quantum entanglement, string interactions, or discrete quantum geometry. If so, bending space-time would describe emergent phenomena rather than fundamental reality. But emergent phenomena are still real. Temperature is real even though it's emergent from molecular motion. Space-time curvature would likewise be real even if emergent. The honest answer combines certainty about observations with humility about ultimate reality. We're certain that gravitational phenomena are accurately described by curved space-time geometry. Observations confirm this across vast ranges of scale and strength. We're uncertain whether this geometric description is fundamental or emergent from quantum structures we don't yet understand. This uncertainty represents the frontier of physics where known meets unknown. It's where science becomes adventure, where equations point toward mysteries, where observation and theory dance around questions too deep for current knowledge to answer. This frontier is humanity's shared intellectual inheritance, the accumulated wisdom of centuries of observation and thought, combined with honest acknowledgement of what we don't yet understand. As we conclude this journey through space-time curvature, remember that you're part of this grand adventure. The questions you ask about reality, whether gravity bends space, what happened at the Big Bang, whether the universe is finite or infinite, are the same questions physicists pursue professionally. Your curiosity connects you to Newton wondering why apples fall, Einstein imagining riding light beams, Hawking exploring black hole horizons. Science is humanity's collective effort to understand the cosmos that birthed us. Each observation adds a piece to the puzzle. Each theory proposes a picture of how pieces fit together. Each generation builds on previous insights while questioning inherited assumptions. The process is messy, uncertain, exhilarating, and profoundly human. Gravity might bend space-time, or space-time might be emergent geometry from quantum information, or the truth might be stranger than either option. We don't yet know. But we know how to find out through careful observation, rigorous mathematics, creative theoretical thinking, and honest acknowledgement when evidence contradicts expectations. This process has revealed atoms, relativity, quantum mechanics, and curved space-time. It will eventually reveal quantum gravity's nature. Meanwhile, Einstein's geometric masterpiece stands as a monument to human understanding. General relativity transformed how we comprehend space, time, matter, and gravity. It revealed a universe stranger and more beautiful than previous generations imagined, a cosmos where geometry is dynamic, time is relative, and massive objects sculpt the very fabric of existence. Whether this fabric is fundamental or emergent, whether future revolutions await or Einstein's framework endures, we're privileged to live when humanity can ask such profound questions and make genuine progress toward answers. We've mapped space-time's curvature around Earth, the Sun, black holes, and across the observable universe. We've detected ripples in geometry from cosmic collisions. We've measured time flowing at different rates and seen light curve through warped space. If you are still watching, make sure to give a thumbs up and subscribe to the channel. And if you enjoyed this video, this other one at the left side of the screen is a must-watch. What happens to gravity inside a neutron star? In this video, discover the mind-blowing science behind the universe's most extreme gravitational environments. See you there.